Okay, so let's check your results. So you graphed this, you put this in your calculator, and then you saw that the domain is negative infinity to infinity. You saw that the function on the right, so as x goes to infinity, rises. So it goes the function goes to positive infinity. And on the left, it falls. Y goes to negative infinity. The x-intercepts were at -2, -1, at 0, at 1, and 2. So therefore the factors were these ones. And then in factored form, you had that the function was this. Now, when you are asked to observe what happens, how does the graph look like with respect to the origin, you notice that if you have a point right here, then immediately the point symmetric with respect to the origin is also going to be on the graph. So if you have a point here, this one is symmetric with respect to the origin being here. So when that happens, so when the graph of a function is symmetric with respect to the origin, we say that the function is odd. And how many turning points do we have? So how many bumps we have? We have 1 here, 2, 3, 4. So we have 4 turning points. And the degree is 5 actually. We'll see that there is a connection between the number of turning points and the degree of a polynomial function. To read more about the even and odd functions, you should read the PowerPoint in section 4.1. You can just click it if you're looking at the PDF, or just go get it from the PowerPoint section. So if you look at 4.1, it gives you more about polynomials, and then it talks about even function having symmetry with respect to the y-axis. So this is another example. So just read this more. Odd function symmetric with respect to the origin. So if you have a point xy, for example, the point with the opposite x coordinate and the opposite y coordinate should also be on the graph. So for example, the point 2, 3 is in here, or yeah, 2, 3 is in here. Automatically the point -2, -3 is also going to be on the graph. So you should read this PowerPoint to learn more about even and odd functions. And then let's solve this problem together. So if the point 6 and -7 and 3 and -1 lie on the graph, yeah, I don't know what's going on, of an odd function, so I have that f is an odd function, then if the point 6, -7 is on the graph, then automatically what's another point? Okay, I definitely have a glitch. Automatically, exactly the opposite, -6. I will be right back. Alright, let's try again. So if the point 6 and -7 is on a graph of an odd function, so we know that exactly the opposite, so -6, +7 has to be on the graph as well. And if the point 3, -1, then exactly the opposite, -3 and +1 has to be on the graph. So this point tells me that f of -6 is 7, and this tells me that f of -3 is 1. Okay? So what is the connection between the degree, the minimum degree, and the turning points? So we can look at the graph of a polynomial, and then depending on how many turning points it has, we can give a lower estimate about the degree of that graph. So for example, the polynomials below have degree 2, actually have 2 turning points. So this one has 1 bump here and then 1 bump here. So this one has 2 turning points, and this one has 4 turning points. 1, 2, 3, and then 4. So the number of turning points basically tells us the smallest possible degree of the polynomial. So if the polynomial on the left must have degree at least the number of turning points plus 1. So the polynomial on the left has degree at least 3, because it has 2 turning points. And then the polynomial on the right must have degree at least 4 plus 1 because it has 4 turning points, so you add 1. You notice that for our previous, we had 4 turning points and the degree was 5. We had 3 turning points and the degree was 4. So in general, if you have like n turning points, the degree is at least n plus 1. So this is what we need to think about. If the graph of a polynomial has n turning points, the polynomial's degree is at least n plus 1. So let's understand what we mean by at least n plus 1. So often this formula gives you the exact degree. For example, for this line is increasing always, so there's not a turning point because it's increasing. It's not changing from increasing to decreasing or vice versa. So it has 0 turning points, and this parabola has 1 turning point. So the degree for this is 1, 0 plus 1, and the degree for the one on the right is 1 plus 1 is 2. But we knew this. We knew that a line is degree 1 and a parabola is degree 2. So in this case, it gives you exactly the degree. However, it is not always exact. For example, this polynomial has 1 turning point, right here. But in fact, its degree is 4. This is actually f of x equals x to the 4th. So it has 1 turning point. It means that its minimum degree is 1 plus 1, which equals 2, but its actual degree is 4. So the number of turning points tells you something about the minimum degree of the polynomial, not the actual degree. So let's look at this last example. Use the graph of the polynomial function to answer the following question. What are the x-intercepts? So we see this is -1, -2, -3. So the x-intercepts are -3, 0. And then I have an x-intercept here, positive 2, so 2, 0. And then 1, 2, 3, 4, 5, 6, 0. Okay? Is the leading coefficient positive or negative? So we know that from power functions, remember that a power function was f of x equals k times x to the p. And if k was positive, and this was a positive integer, the graph was like this. And then if k was negative, it flipped about the x-axis. It was like that. So basically, the same principle here. We're going to say that the leading coefficient is positive. Okay? So if they both go down, so if this was the other way, going down like that, then we would have said that it was negative. So let's just now put that in there. What is the minimum degree of f? Well, the minimum degree, well, look at how many turning points we have. We have 1, 2, 3. So the minimum degree is going to be 3 plus 1, which is 4. Okay? So this has minimum degree 4. For polynomial regression, you're going to look at the notes in PowerPoint 4.2. Here, you click here if you have the PDF, or you just go to 4.2 in the PowerPoint. I'm meant to open it. There you go. It tells you more about each specific polynomial. So you have the constant polynomial, it's just a horizontal line. The linear polynomial, which is just your basic ax plus b. Quadratic polynomial, it's your parabola, and then the cubic, and so forth. So you definitely want to look over these. But what I wanted to show you is how to use polynomial regression. So just make sure you look over this example. So you're going to model this data with a polynomial. and it says to find a polynomial of degree 3. Well, degree 3 is called cubic polynomial. So you'll see in here, when you do your regression, you're not going to pick linear regression or quadratic regression, you're going to pick cubic regression. So that's all you're doing different from the other types of regression. So you're going to keep the cubic regression, and then basically it gives you the result. So it gives you the coefficients. The leading coefficient is 0.00138 and so forth. So this is what you're interested in to see. So make sure you look over this example. Okay, so okay, also I read PowerPoint 4.4. This basically just talks about the factor theorem, and we've mentioned it before, we just didn't call it factor theorem. So it goes down to, if you have it in general form, like x to the 5th minus 10x cubed plus 9, and then we saw that in factored form it was x minus 3 times x minus 1 times x plus 1 times x plus 3. Okay, so the factor theorem basically says that if 1 is a 0, then x minus 1 is a factor. That's all it says. But if you need more explanation, read this short PowerPoint on section 4.4. Okay, so what you need to remember for polynomial function is how a polynomial function looks like, how to get the degree, what is the leading coefficient telling you if it's positive or negative, how to graph these, and how to read the zeros and the factors from the graph. And then you need to know about the minimum degree and the turning points.